if the force applied to the lowest string increases slowly, as shown on this graph number 1. If we pull down slowly, harder and harder, increasing the force, then the upper string will break, because the tension in the upper string is always larger than the tension in the lower string. Now, what happens if we pull the lower string sharply and quickly, increasing the force F? What happens in this case? The equation will be the same, because the second Newton's law is the universal law applicable in such cases of mechanical processes. The equation will be the same because the forces are the same, but the acceleration of the sphere will not be zero. Why? If we pull quickly, then what happens? The force acting on the sphere increases very quickly, and the sphere actually wants to go downward, wants to accelerate, and it starts accelerating. But something is prohibiting the sphere from going far. What is it? The upper thread. But the upper thread is anyway stretchable. It can be stretched. It can be elongated a little bit, as any material. There are no unstretchable materials. Any material, anything may be elongated if you apply force. So the upper thread may be elongated just a little bit. It's stretchable. And if we pull very quickly, the sphere wants to go down and it wants to accelerate, and it will start moving, and the upper thread will be elongated just a little bit. And so the acceleration of the sphere will not be zero. And in this case, we may observe, this can be easily proven experimentally. The experiment is very easy. You can do it at home. You can take a heavy object, suspend it on a thread, and then similar thread should be attached here, and then pull it down quickly, and you will see that the lower thread will be broken, and the upper thread will not be broken. But if you pull slowly, the upper thread will be broken. So the explanation is just in this equation. If we pull quickly, the sphere will start accelerating because the upper thread is stretchable, and it will be stretched a little bit. It will be elongated a little bit, and so the acceleration will not be zero. And if the lower thread was broken, then, if it was broken actually, then of course the tension in the lower string was larger than the tension in the upper string at some moment in time. So if the lower thread is broken, then F is larger than T at the moment of breaking thread. And if F is larger than T, then from this equation we find that MA is larger than mg, because F is larger than T, and the difference will be some positive number, some positive value. And so MA will become larger than mg. And in this case, acceleration of the sphere A will be larger than g for a very short moment of time, very short period of time. The sphere will be accelerated downward with acceleration larger than g. And in this particular case, if A is larger than g, then the tension in the lower string will be larger than the tension in the upper string. And in this moment, the lower string may break, while the upper string will remain intact. You can do this experiment at home. You can take a thread and suspend a heavy object on the thread, so heavy that the thread is not broken immediately. And then attach a similar thread here, and then pull it quickly downward, and you will discover that the lower thread is broken, while the upper thread is not. But if you repeat this experiment and pull it slowly, then the upper string will be broken. How do we explain it? Using the second Newton's law, and taking into account that the upper string is stretchable a little bit. Its length may be changed just at very small quantity, and so the acceleration may be other than zero for a very short period of time. Such short period of time that the sphere will not actually be displaced. We will not notice the displacement. It will be very small, just less than 1 millimeter, just a few microns. It will be displaced by just a few microns. We may not notice it, but we will just notice that the upper thread remains intact while the lower thread breaks if we pull quickly. But if we repeat the experiment and pull slowly, then the picture will be different. The upper thread will be broken. So this is a very easy mechanical experiment which I advise you to repeat at home. I urge you to do this experiment and watch yourself what happens here. Okay. Another problem from Buchovtsev that we will consider now is problem number 62. Problem number 62. It says, a bead of mass m is fitted onto a rod with a length 2L. So we have a rod which is, I suppose, which is made of thin wire, probably, and a bead is fitted on the rope. What is a bead? Is a small sphere with a hole in it, a small spherical body with a hole inside, so that we can fit the bead on this wire, and the bead can slide along the wire without friction. So a bead of mass m is fitted onto a rod, and the length of rod is 2L, and the bead is in the center. At the initial moment, the bead is in the middle of the rod, is in the center. The rod moves horizontally in a horizontal plane with an acceleration a, directed in direction forming an angle alpha with the rod. So this is a horizontal plane, like the plane of the surface of this table. Everything which is drawn on the blackboard happens in horizontal plane, so that the bead will not slip down. And the rod is accelerating, moving translationally at some angle alpha, and the acceleration is directed at the angle alpha to the rod. Find the acceleration of the bead relative to the rod. Acceleration of the bead relative to the rod. So we have to find acceleration of the bead relative to the rod. I will indicate this fact using the letter R, which says that this is the acceleration of the bead relative to the rod, not relative to the earth. Also find the reaction force exerted by the rod on the bead, reaction force, and the time when the bead will leave the rod, and some time when the bead will leave the rod. Why the bead is going to leave the rod? Because if you move the rod in this direction, the bead will somehow slip in this direction, and then it will slip off and leave the rod. Because there is no friction between the bead and the rod. There is no friction. Certainly, if the rod is placed here in such direction and accelerates perpendicularly, then the force acting from the rod on the bead will be directed here, and the bead will not move with respect to the rod. It will stay where it is on the rod. Also, if the rod is directed in such a way, accelerated along its length, then the bead will slip very quickly because there is no friction between the bead and the rod. The rod accelerates here and the bead remains where it was. It remains at rest. And then the rod slips away and the bead remains here. So the bead will quickly go off the rod in this case. But we consider some intermediate situation when the acceleration is directed at some angle to the rod. Angle alpha is also given to you. Alpha is given in this problem. So this is problem number 62. I wonder if it's included in your home assignment. 62 years. This problem is from your home assignment. So sometimes I will solve problems from your home assignment so as to help you, as to explain to you how you must solve some problems. Okay. So how we consider this problem? First of all, note that there is no friction between the bead and the rod. If there is no friction, that is the force directed along the rod, if this force is zero, then the only force of interaction between the bead and the rod can be directed perpendicularly to the rod. No other way. This force cannot be directed at some angle, because at any angle other than the right angle, because there is no friction between the bead and the rod. So the rod moves in this direction, and the only force acting on the bead will be directed perpendicularly to the rod. And so the bead will move due to the forces acting on it. And the only force acting is this one. So the bead will move along this direction as the rod moves here. So at some moment in time, the rod will be here because it's moving translationally, remaining parallel to itself. This new position of the rod is parallel to its previous position. And the bead is slipping off the rod, and at some moment of time, the bead will leave the rod, will slip off its end, because the bead moves here and the rod, and this place of the rod moves here. What do we know here? We know that the length of the rod is 2L. So this half of the rod is just L. This angle is alpha. It means that we know all other fractions. For example, this larger leg of this right triangle, the larger leg, if the smaller leg is small l, then the larger leg may be denoted by a large L. the larger leg may easily be found because the larger leg divided by the smaller leg will be tangent alpha. So the larger leg is known. Small l tangent alpha. Also, this point of the rod will somehow be displaced to another point. Let it be point A and this point B. So point A in some period of time will be found in this place B, and this point will cover distance s, and distance s can easily be calculated because L, the small leg divided by s, by definition is cosine alpha, and therefore distance s covered by the rod during this period of time is L divided by cosine alpha. So we know distance s and we know this distance L covered by the bead from geometrical considerations. Okay, we know the distance of displacement of point A, and we know the acceleration with which point A moves. So we can use the formula for distance covered by a uniformly accelerated point, which is the distance is what? Acceleration times t squared over 2. And from here we can find everything is known. S is known, acceleration A is known because it's given in the statement of the problem. So we can find time. Time period which is required for point A to move into position B. Time t will be what? Square root of 2s over A, which can be expanded like 2L over A cosine alpha. So we have found the time needed for point A to move to point B. But during this period of time, the bead will move from here to here and will slip off the end of the rod. So this is the time of life of this bead. This is the lifetime of the bead on the rod. In this period of time, the bead will go off the rod. So in this time, the bead will cover the distance L, which is known to us. L is known. We know the time, and we know that the bead will move with uniform acceleration, constant acceleration, but we don't know this acceleration. Okay? So we can express the distance covered by the bead from here to the last moment when it's on the rod. The distance covered by the bead, L, is what? Acceleration of the bead. This is absolute acceleration with respect to the ground, with respect to the earth, t squared over 2. We know t. We have found it. We know the time of the lifetime of the bead on the rod. So we can find acceleration of the bead from here. Acceleration AB. Note that I am using different notation. This is acceleration of the bead, and what we need to find is the acceleration of the bead relative to the rod. But this is not the acceleration relative to the rod. This is the acceleration of the bead relative to the laboratory reference frame, that is relative to the Earth. And we can easily find it from this equation. So AB will be 2L over T squared. Well, we know L, we know T squared, no problem to calculate it. How can we find acceleration of the bead relative to the rod? Relative acceleration. We know that during this time interval, the bead moved from the center of the rod to its end. The bead actually moved from the center, this point, with respect to the rod. The bead moved from here to here. That is, the bead displacement was L with respect to the rod. It was L small. And it was capital L displacement with respect to the ground, to the laboratory reference frame. And with respect to the relative to the rod, the bead displacement was small l. So if the bead displacement was small l, and we know the time period, and we know that the acceleration was uniform, it was constant, we can easily find the acceleration of the bead relative to the rod, AR, using the same formula. Twice the displacement over T squared. As we need to calculate it, let's do it. 2L over T squared, and T squared is easily found from here. That is 2L A cosine alpha. 2L will cancel, and the acceleration of the bead will be A cosine alpha. So this is the answer to the first question of our problem. We have found acceleration of the bead relative to the rod, because we have found the time period needed for the bead to slip off, and we have found the displacement of the bead relative to the rod. And using this simple formula for the displacement can be expressed using acceleration and time. So this kinematic formula is well known to you. The distance covered by a uniformly accelerated point in time t. From this formula, we found this relative acceleration. And because every physical quantity included in this formula is known, we have found time t, and we know L it's given, then we can easily calculate the acceleration of the bead relative to the rod. What else? We need to find N, the force acting on the bead from the rod. In order to find N, we have to use the second Newton's law, the mass of the bead and its absolute acceleration with respect to the laboratory reference frame, that is, acceleration of the bead. It's not the acceleration relative to the rod. This is the acceleration relative to the ground. And we have to multiply this value by the mass of the bead, and that will give us the force acting on the bead. So the force can easily be calculated from using this formula. That will be the mass of the bead times acceleration AB, which is known as 2L over T squared. And we know L is small l tangent alpha. Why do we have to substitute it? Because large L, capital L, is not given in the statement of the problem. It's not given, it's unknown. We have to use, finally, only the physical quantities which are given in the problem, given to us. L small l is given, and alpha is given. So we have to substitute this formula for capital L. So 2 capital L, which is small l tangent alpha, times mass over t squared, and t squared can easily be found from here. This is 2l times a cosine alpha. 2l cancel, and tangent is sine over cosine, so cosine will cancel, and what we have is acceleration of the rod times am, acceleration times am, and 2 is here also, and tangent is sine over cosine, so cosine will cancel, so the only thing remaining here is sine alpha. So that is the answer to the second question. The force acting on the bead from the rod, this force is responsible for the bead acceleration in which reference frame? In any inertial reference frame. The inertial reference frame is usually the laboratory frame, which is connected to the Earth. And so this is the inertial acceleration relative to inertial reference frame. And the rod itself is not an inertial reference frame because the rod is accelerating. And as it's accelerating, it's not an inertial reference frame. So in order to find this force acting on the bead from the rod, we have to use the inertial reference frame and the acceleration of the bead relative to the inertial reference frame. For example, reference to the Earth. Also this problem requires to find the time, the lifetime of the bead on the rod, the time interval after which the bead will slip off the rod. And we have already found this time. That is the answer to the last question of the problem. With the only difference that here I denoted this time as tau, and here I denoted it as t. So t equals tau. Just it's not a good practice to use different letters to denote the same physical character, but sometimes it happens. Sometimes it happens, and I did this in this problem. I denoted the same physical quantity using 2 different letters. Okay, no problem in case I noticed it. In case this did not lead to a mistake. No problem. Where? Here? AM sine alpha? Yes, certainly. Yes, certainly. 2 cancelled. Yes. I crossed it out here and I have forgotten about it here. Yes, you're right. 2 is cancelled. Yes, certainly. Any questions regarding the bead on the rod? The bead on the rod. How it slips along the rod without friction? The question to you, why should we consider this problem in the horizontal plane? Why we cannot consider the same thing in vertical plane, for example? Why this is the horizontal plane? This, I told you, this picture is refers to the surface of the table, for example. Why so? Why can it not be? Why the solution would be wrong if the rod is located in a vertical plane, like in the plane of the blackboard? Because in vertical plane, we will have to take into account the gravitational pull. But if this is a horizontal plane, then gravitational pull is directed this way, and it's balanced by the force of reaction from the vertical force of reaction from the rod. And these two forces cancel each other without any consequences because there is no friction. That's it. Where did we use Newton's laws here? We used a lot of kinematical formulas expressing the displacement versus acceleration in time. And we used a lot of geometrical formulas expressing the legs of the triangle, right triangle, using geometrical functions, trigonometric functions. So where did we use Newton's laws? Here, the only place where we made use of the second Newton's law. The force acting on the bead equals its mass times acceleration. Acceleration in any inertial reference frame. For example, reference frame associated with the Earth. This is not the acceleration of the bead in the reference frame connected to the rod. If you consider acceleration in the reference frame connected to the rod, then it will be a different quantity, AR. It's a different value. Acceleration AB is A sine alpha, and acceleration AR is A cosine alpha. Different accelerations in different reference frames. One reference frame is inertial, another moving rod is not inertial because the rod moves with acceleration. Another problem, let's consider problem number 63. What if we use this part of number 63? Solve the previous problem, assuming that the moving bead is acted upon by a friction force. The coefficient of friction is given. It's K. The coefficient of friction between the bead and the rod. Again, disregard the force of gravity. That is, again, we consider the same problem in a horizontal plane. But now we add forces of friction. We disregarded friction in the previous solution, but now we will take friction into account. So the same problem, but forces of friction added. How to solve it? There is an elegant way to consider such problem. Let's go to the reference frame associated with the rod. That will be a non-inertial reference frame. So imagine that you are sitting on this rod, and the rod is at rest with respect to you because you are sitting on it, and you are accelerating together with the rod. What happens with you if you are accelerated, for example, in a car? You are sitting in a car and the car is accelerating. What's happening to you? Some force tends to press you against the seat of the armchair, right? Something is pressing you backward. That is the force of inertia, which emerges in any accelerating reference frame. And the same case will be here. So we consider that we are sitting on this rod, and there are some forces of inertia directed opposite the acceleration of the rod. So if the rod is accelerating here, then all forces of inertia will be directed here. The force of inertia acting on the bead will be directed here. And the force of inertia will be MA acting on the bead. It will be MA. The same situation happens when we are standing on the Earth. If the rod is in such a position and the bead is here, there is the gravity pull force, which is mg. In our case, the rod accelerates upward with acceleration a, and gravity should not be taken into account because everything happens in horizontal plane. So instead of gravity, we must use the acceleration a of the rod. And this will be the inertial force acting on everything on the rod in this reference frame connected to the rod. Imagine you are sitting here, then you will observe this force of inertia acting on the bead. That is the best way, I think, to solve this problem, to go to another reference frame. In this particular case, we go to the reference frame connected to the rod. This reference frame will be non-inertial because the rod is accelerating. And in this non-inertial accelerating reference frame, there will be a force acting on the bead, directed in the opposite direction, opposite to the acceleration of the rod. And the situation becomes very similar to what? To an inclined surface. We have solved this problem. We know what forces act here. Instead of gravitational pull, now we have the force of inertia, and instead of acceleration of free fall, we have the acceleration of the rod, but nothing else is different from the problem which we solved earlier. We considered the block on the inclined surface, but what's the difference? No difference at all. The same thing. With the only difference that now angle alpha is here and this angle is not alpha. This angle will be no, angle alpha is not, no, this one, the angle alpha is less than 90 degrees. So alpha is this angle. Alpha is here. And this is incorrect. Angle alpha is here. Then this angle will be the right angle minus alpha. And we may denote it as beta, the angle of inclination of our imaginary inclined surface. And so the acceleration of anything here will be given by a formula which we know, which we considered last time and which I discussed in the very beginning of this lecture. We found this acceleration, an acceleration of the bead with respect to the rod, acceleration AR. That's what we must find now, acceleration AR. I just repeat the formula which we have obtained for the inclined surface. The formula which we obtained looked in this way. G acceleration of free fall sine of this angle, which is now beta, minus coefficient of friction cosine of the same angle beta. Now, instead of acceleration of free form, we have to use acceleration of the rod. And we have to express beta somehow using alpha. So what we have now in this problem, acceleration of the rod, sine beta will be cosine alpha. I remind you that sine pi over 2 minus alpha is equal to cosine alpha minus coefficient of friction, and cosine beta will be sine alpha. So that will be the answer to our problem. If we take into account friction forces here with some coefficient. The problem, this new problem with the rod, is reduced to the old problem with the inclined surface and the block on the inclined surface. That is the best way to consider this problem. In the same way as we have found the acceleration of the bead relative to the rod, we can modify all the formulas of the previous problem to take into account forces of friction. What will be changed in the new formulas for this particular problem? Instead of the terms acceleration times cosine alpha, we will have to use this formula which includes the coefficient of friction. So we substitute this formula for any expression containing a cosine alpha. Instead of a cosine alpha, we will have to use in this new problem a cosine alpha minus k sine alpha. So the expression will be slightly more complicated. For example, the time of life of bead on the rod will be what? Will be 2L if we take into account coefficient of friction cosine alpha minus k sine alpha. That's it. We will have to use, instead of the old formula for the acceleration of the bead AR, we will have to use this new formula, and nothing changes, just like using new expressions for this expression. So that will be the answer to the question, what is the lifetime of the bead on the rod if we take into account the coefficient of friction between the bead and the rod. I think we will have some time to consider another problem. We will have 10 minutes before the end of this lecture. And another problem will be number 65. Number 65. A wagon of mass m moves without friction over horizontal rails at a speed of v0. So a wagon or a railway car, something like that, moves on horizontal rails without friction with velocity v0, which is given. The mass of the wagon is given. A body of mass m is placed here on the front edge of the wagon, on the very front edge a small body of mass m is placed without any initial velocity. The initial speed of the body is 0. So the wagon is moving, and we just place the body here at the front edge of the wagon. At what length of the wagon will the body move? At what length will the body move? And the main question is, what should be the length of the wagon? This length. What should be the length of the wagon? So that the body remains on it and does not slip off the wagon if the coefficient of friction is given. The coefficient of friction between the body and the wagon surface and the platform surface, well, is given, the coefficient of friction. So there is a force of friction between the body and the wagon. It's obvious that if there is no friction, or if the friction is very small, then the body will slip along the surface and then fall down. But if the friction is high, then the body will slip along the wagon and then stop on it. Moving with it, yes, it will accelerate and move together with the wagon. So if the wagon moves here, then the force of friction acting on this body will be directed in this way. And according to the third Newton's law, equal and oppositely direction force will act on the wagon. I use the same character F, but different directions of vectors acting on these bodies. So the acceleration of small body will be force of friction over m. And the acceleration, or let it be acceleration of the small body, a1. And the platform experiencing the same force but in the opposite direction will have also some acceleration in the opposite direction, a2, which is the same force of friction over the mass of the wagon, a2. So as the wagon moves, the small body accelerates in the same direction with this acceleration, a1, and the wagon experiences the same force but in the opposite direction, and so the wagon will have opposite acceleration, a2, which seems to be much smaller because the force is the same, but the mass of the wagon is much larger. So the acceleration of this wagon will be smaller. What will be the velocity of the small body? The velocity of the small body as a function of time will be, the initial velocity is 0, so it will be acceleration of the small body multiplied by time. And the velocity of the wagon as a function of time will be the initial velocity, which is v0, minus acceleration of the wagon a2 by time. So the small body accelerates, increasing its velocity, while the wagon decelerates and decreasing its velocity. When the small body will stop on the surface of the wagon, when they will have the same velocity. So when at the moment of time when velocity v1 equals the velocity v2, at this moment of time, when the velocities are the same, the small body will stop on the surface of this wagon and will not slide on the surface. The slipping will stop. So if we need to find when the slipping is over, we must write the condition when the slipping stops. From here, we can write that a1t equals v0 minus a2t. This expression should be equal to this expression. This is the condition for a time moment at which the slipping stops, the slipping of the small body on the surface of the wagon. So the time can easily be found from here, this time interval. The time of slipping can easily be found. That will be V0 divided by A1 plus A2. But what is A1 and A2? We know well, A1 plus A2. So this is V0 divided by F over small m plus F over capital M. That is the time interval during which the small body slips on the platform, on the surface of this wagon. And it stops, slips and stops somewhere. Whether the small body will stop on the surface or fall down from the wagon, it depends on the way, on the distance covered by small body and distance covered by the wagon. So we have to calculate distance covered by the small body and the distance covered by the wagon in this time interval. So the distance covered by the small body, let it be S1 covered by small body. Everything related to small body will have index 1. So the distance covered by the small body will be what? It's acceleration A1 t squared over 2. And the distance covered by the platform during the same time period will be its initial velocity t minus acceleration of the wagon t squared over 2. So to put it on the graph, this is the wagon and this is the initial position of the small body. The small body is accelerating and it covers this distance until it stops. At the same time, the wagon goes here with deceleration, but it goes somewhere to this position. So this point, the front of the wagon moves here. So this is distance S1 and this is distance S2. And so if the difference between these two distances S2 minus S1, if the difference is smaller than the length of the wagon, if it's smaller or equal, then the small body will remain here. But if the difference between these two displacements, if the difference is larger than L, certainly, then if the difference is very, I was right originally. It should better be said that if L is larger than the difference, that is the difference between the two displacements. If L is larger than this difference, S2 minus S1, this is S2 minus S1. If the length of the wagon is larger or equal to this difference, then the small body will remain on the wagon and will continue moving with it. But if the length of the wagon is smaller, then the small body will flip off the surface of the wagon and fall down on the rails. That's it, the main idea for solving this problem. We know S2, yes, we know it. All the quantities here have been calculated. And we know S1, certainly. We have calculated A1 and we have calculated T, so no problem in substituting these quantities. This one should be substituted here, and this quantity should be substituted for S2, and no problem in finding difference between these two expressions. This is just a simple algebra. Any problem you solve always consists of some physical considerations, and then after you have used all the necessary physical considerations, then you have to solve some mathematical equations. So any problem is divided into two parts, the physical part and mathematical part. We will consider and discuss the physical part, but not always the mathematics. Not always. It's so simple, it's just algebra, you can do it yourself. Do it please yourself, it's not a big problem. And this problem number 65, which we have discussed, is also a part of your home assignment. So we have actually discussed this problem. Okay, let it be the end of our lecture. That's the end for today.